Okay. Yes, okay, so welcome to the last lecture. So I wasn't sure if I wanted to do it, but actually let me, not the last lecture, what I'm talking about. So I think I will discuss a bit what happens to these beta equations. Okay, I think it's kind of nice and useful for sure. So I was saying today that you get this. So if you want to construct the eigenstates of the XXZ chain, you have to solve this very nasty set of nonlinear coupled equations. So to appreciate how difficult this is, so you should remind yourself of the fact that this set of equations contains 2 to the L set of solutions, because here there is the whole set of eigenstates of the XXZ chain. So it's really a huge number of solutions. So if you dare to try to solve them numerically, this is a nightmare. So there is no way to do it in an efficient way. So also another thing that you should know is that the solutions of these equations are not real. You have complex solutions, so it's even worse. So you have the complex plane, and then the solutions somehow are there. And you might say that, okay, they can be distributed in a random manner, so there is no hope of trying to study the structure of the solutions. Still, you can do something which is also useful if you have in mind of going to the thermodynamic limit, which is what actually I have in mind. So, and you can take the log of these equations, and you see that immediately there is a nice thing that happens, that this product becomes a sum, which is good. And then you can change variables. So these are the momenta. You can define something that is called rapidity. So, and then you can look in the complex plane what happens to these rapidities. So actually, so you realize, and this was realized actually early on by Bethe in 1931, that you can have real solutions that lie on the real axis, but you can also have complex solutions. But these complex solutions are not completely random. So they have a particular structure. So for instance, you can have solutions that appear like that. So, okay, they form a kind of string. Okay. You can also have more complicated structures, like something like this. Okay. So they have somehow the same real part, and then they are equally spaced along the imaginary axis. So the thing is that I'm lying, okay? It's not true. So this is true only in the thermodynamic limit, and it's not true for all states. So you take the limit L going to infinity, and this is actually how Bethe realized that this kind of equations have that type of solutions. And then what you can see is that, so the majority of the states have this pattern, okay? So either they are real, or they lie on these strings. No, this is discrete. Yeah. So in fact, this is a good point. So this distance here it becomes a simple function that you know in the thermodynamic limit. In fact, this is a good point, because then this means that the only thing that you need to care about is only this real part. Because then once you know the real part, you can build the states, the solutions in the multiplet. So first of all, what are these kind of configurations? These are the famous bound states that I was telling you at the beginning. And this you can guess easily, because you have something with an imaginary part. So if you substitute into the expression for the ansatz for the wave function, you get something that decays exponentially. So in this case, you get that the two downspins, they want to stay bound together, behave as a single particle. In this case, you have a larger bound state. Okay. Good. Okay, now, as I was saying, so if you believe in this string structure, which is not true in general, okay, it's an approximation which holds for the majority of states in the thermodynamic limit. I mean, if you believe it, you can write an effective set of equations for these real parts, okay? For the so-called string centers. So, and this somehow lead to a slightly more friendly system of equations. But I think the important thing is that this interpretation of these objects like bound states, I mean, it's important for I mean, it gives a nice way to classify the solutions according to their physical meaning, okay? Okay, so now let's make the big step. So we want to go from this discrete set of solutions, so from these equations on a lattice in the thermodynamic limit. And here actually we see what Benjamin was telling us in the morning. So this is like when you have these two clouds of gas, and then if you want to look at individual particles, it's a mess. And here, if you want to look at individual solutions, it's a mess, right? But if you look at thermodynamic quantities, like if you look at these blobs as a whole, then the physics might become simpler to understand. Okay. So when we go to the continuum limit, when we go to the thermodynamic limit, so instead of working with this rapidities lambda, we define their densities, okay? So we have a rho particle of lambda, then we have a rho whole of lambda, and then we also have that we have a rho total of lambda, which is rho particle plus rho whole. So, and here the interpretation is like here, you know, I mean, rho particle is the density with which you occupy these single particle levels. You can also put holes, but then since you are interacting, rho particle plus rho whole is not a trivial, because you are interacting, unlike free fermions. Good, so we are going towards thermodynamic Bethe ansatz. This is what I want to briefly summarize. Okay, this is a quite old subject, and there is an excellent book about it, which is the book of Takahashi, is Thermodynamic One-Dimensional Solvable Models. Well, 1D solvable models. Okay, there is also a long paper on the archive, which where you can find these things. Okay, so the main objects that we want to deal with are these three densities. So from these three densities, you can define an entropy, okay? A thermodynamic entropy, which is Yang-Yang entropy. Yang-Yang entropy. And this is, sorry, an important thing that I should say, which is fundamental, but I forgot. So the fact that we classify these solutions according to their, to the bound state, to this bound state, in this bound state motivated manner, means that here we have an extra index, n, okay, which labels the different type of bound states. So if then this n is 1, it means that we are working with the real solutions. If n is 2, I'm just restricting to these two particle bound states and so on. Okay, and you can have that n goes from 1 up to infinity, well, depending on the model you have. Okay, so the thing that I want to introduce is the entropy. So the entropy is d lambda rho total. Well, here you have a sum over n, rho n log rho total n minus rho particle log rho particle minus rho whole log of rho whole. Now, so if you did the exercise that I gave you in the morning, you would have found this expression. Okay, so if you remove rho total because it's a trivial, and you replace rho whole with the minus 1 minus rho particle, then you recover the free fermion expression, right? So of course you have, this rho becomes the n of k. Here you have also this rho total, and rho particle and rho whole now are independent. So what is the physical meaning? So the physical meaning is that this set of densities correspond to a thermodynamic macrostate. So now if you go back at the picture that I was drawing at the beginning, so you have the spectrum of the Hamiltonian, and then you have your generalized macrocanonical window. Okay, so basically what happens, for instance, if you fix the energy, is that all these eigenstates will give rise to this same set of density. Okay, or yeah. So, and what is this entropy? Is that it has the same meaning that the usual entropy has. So the number of eigenstates here scales as e to the ls. Okay, and this is this S Yang-Yang. So this entropy gives roughly how many states you have with fixed, well, here energy if you are working with the Gibbs ensemble, or GGE if you are working with the generalized Gibbs ensemble. So, okay. Now let me write down just a few equations. So this is really a crash course on TBA, a few minutes. Okay, you have a certain set of densities. Which constraints do you have to put on them? Are they allowed or not? Of course, since these lambdas satisfy the beta equations, you might imagine that there are some constraints. So a simple constraint you can get by taking really the thermodynamic limit of those equations. And if you do that, you get this equation. I always forget this P. Let me call it M. Infinity. Okay. So given a set of equations, given a set of densities, rho whole, rho particles, they have to satisfy these equations. Yes, sorry, indeed. Yeah, thanks. Okay, so they've satisfied these equations, and here, I mean, all the Bethe-Ansatz models that we use, or at least most of them, they obey some kind of equations like that. And so to select a particular model, you have to provide this information. And the most important information here is this T, which encodes the scattering between the different quasi-particles. Okay. So this is basically asking that this set of densities correspond to some coarse-grained version of an eigenstate. Okay. But now you want to do something different. You want to work with the statistical ensembles. So let's say that you want to work with the Gibbs ensemble. So Gibbs ensemble, like this, 1 over Z, okay? So what do you do? So to construct the Gibbs ensemble, you need to have a sum over eigenstates. Sum over eigenstates, and then you need this e to the minus beta h. Well, let's forget for a moment about, okay, the normalization, let's put it. Now let's go to the thermodynamic limit. Okay. So let's go to the thermodynamic limit. Everything is falling apart. No, okay. Bethe-Ansatz doesn't do this to you. Okay, so you go to the thermodynamic limit. So now a key thing is that you can replace this sum with a functional integral, okay, over this set of densities rho. And then here you have something, beta h, let me call it E, energy, which is also a function of rho, okay? And then, you know, since you are going to the thermodynamic limit, each rho corresponds to e to the Ls states. So here you have some L, S, okay, this S yang is the entropy per site, because the entropy is extensive. So the energy is also extensive, so let me put something here, an L. Okay, and then you take the limit of L going to infinity, and then you see here you have L, so you do saddle point. Okay. Okay, you can do it, and so if you do it, you get these equations. Actually, before writing down, let me comment again that here the most important thing is that you have the quasi-particles, right? Because, you know, you can write something like this for a generic system, but it's not so easy then to do saddle point in practice, right? Here you have quasi-particles, you have these distributions of quasi-particles. This make life easier. So if you do the saddle point, you get these equations. Let me define this. Now this is particle. Okay, let me define these filling functions, eta n, which is the ratio between rho whole and rho particle. So the saddle point gives this. So okay. Okay, now, so you have an equation for these etas, and then here you have this G. This G encodes the information about the ensemble. So if you work with the Gibbs ensemble, it's basically beta times energy. So if you work with the GGE, it's something else. And the key problem in solving the quenches is to determine what is this G, which is called driving. Sorry for the experts, this might sound really completely easy, but okay. Okay, good. So basically, this is this is enough if you want to work with ensembles in integrable systems using TBA. So another thing that I want to mention is the following. So because I need it for the quasi-particle picture. Okay. So if you remember, for free fermionic models, we defined the group velocities of the quasi-particles. I mean, we use the definition of group velocity, which is d epsilon over dk. So what do we do here? The natural thing that you might want to do is the following. So you take your dispersion, you have your single particle energies, and to calculate the velocity, you have first to think of what happens if you create a small perturbation here. And the small perturbation means that you do a particle hole. So in a free fermion model, this doesn't do much. You see, because all particles are independent. So if you do it in a generic interacting integrable model, as soon as you change one particle, since all the particles, the rapidities are related via the beta equations, all the others get rearranged. And this gives, a finite effect. So in practice, this gives a renormalization of the bare velocities of the quasi-particles. So you take your integrable model, you have an expression of the energy as a function, or of rapidity or of momentum. You can define a bare velocity, which is v bare, which is a function of n and a function of lambda, which is derivative of epsilon bare well, actually, you have to to take the derivative with respect to the momentum. So let me remove this, but it's not a big issue. Okay. Yes. Did I want to say? Okay. Yeah. And these are this epsilon is just you get it from the beta. You get it from the beginning, right? So it's basic information about the model. So the fact that when you perturb with the particle Hall excitation one single particle state, all the other rearrange, means that you go from this V bare to something that is called V dressed. Okay. So how do we determine this V dressed? So this V dressed satisfy again another integral equation, which is here. So V dress n is equal V. This is horrible here. V bare sum over m integral over d mu t mn lambda minus mu divided this m, no, this is n lambda rho m particle mu. Okay, so this is an integral equation that allows you to sorry, here there is a plus. Yeah. Yes. So you have a way to feed in the bare velocities and get out the dressed ones. So there are several ways actually to write this equation. So at least 2 ways. So this is the one that maybe is easier to explain because it has a simple physical meaning. Because you see, if you look at this term here, where you have the difference between the dressed velocity with the rapidity lambda minus dressed velocity with rapidity mu. So this is basically the multiplied by the root density of the particle with the rapidity mu is basically giving you the number of scatterings that the particle with the rapidity lambda experiences due to the presence of other particles with rapidity mu. Okay, so actually you can really draw a picture like this. So you are given an ensemble which can be Gibbs, GG, or whatever, which is characterized by these densities rho. This you can interpret really as the density in real space of quasi-particles. Then you might imagine of taking a particle with the rapidity lambda and the velocity v bare. So this particle starts traveling with bare velocity. Then it has to scatter with the other particles with the rapidity mu. And each time it scatters, its position is shifted by this object here, which is related to the scattering phase. Okay? So it does like this. So here, for instance, it scatters with another particle, and then it goes on for a while with the bare velocity, and then it scatters again, blah, blah, blah. It scatters again. So as a result, while the particle with the bare velocity would be here, due to the scattering, so its trajectory is shifted. So it's like it's moving with a different velocity, which is this v rest. So you can actually, if you want to do dynamics in an integrable model, you can actually run a Monte Carlo simulation using this trick. So it gives a nice physical picture of what's happening. Good question. I think it might depend on the T. Yeah. Yeah. Yes. So actually, Benjamin, I think will explain this much better in greater detail. So now, so what are the consequences for the quasi-particle picture for the entanglement dynamics? So for interacting system, an important thing. So let me see if I have it. Where did I put it? Okay, I don't remember, but what I wanted to say is that so for ground states, actually this equation, I think, or a similar equation is already in Koryepin, Bogolyubov, his urgent book. For generic state with the finite entropy, so the first time that I saw it was in this paper by Bonds, Fabian, and Andreas Leuchli. And this is, I think, a PRL, 2000, 13. Okay. And if you go to the appendix of this paper, you find actually a derivation of this equation. It takes more or less half a page to derive it. Okay. So most importantly for us, what is the consequence of this fact for the entanglement dynamics? So we have the quasi-particle picture. Now, so we do a quench, and then the steady state is described by a certain GGE. Now, the entropy carried by this quasi-particle pairs is the thermodynamic entropy of the GGE. But now you see, these quasi-particles are assigned this entropy, but they move in the presence of other quasi-particles, so they scatter with each other. But you can absorb all the effects of the interactions in the redefinition of their velocities. Okay. Okay. So what is left? I shouldn't have removed this, but too late. So what is left is the most complicated thing is to solve the quench. So finding the set of root densities that describe the GGE that gives you all the information about the steady state. So this is really non-trivial. So the way to do it is to take the TBA equations that I wrote before for this filling functions. So you have log eta equal to gn lambda plus the second term that comes from the scattering. So, and you should be able, if you want to solve the quench, to determine this gn. Okay, for a thermal state you know it because you put it yourself by hand. For a quench, somehow you don't know it, because in principle, if you want to write it in terms of conserved quantities, this is something like, okay? But you don't know how to fix in an easy way these parameters, these lambdas. So there is a way out, which is, actually there are several ways out, and I think here I should apologize because I will present only one of them, which is the one that is more familiar to me. And this is via the so-called quench action. Okay, so okay, actually the idea is simple because this morning Benjamin wrote an important formula, and this formula was this. So you have an observable and its expectation value in the steady state, or after taking equivalently after taking a time average, is this. Okay, so it's described by the diagonal ensemble, and the important thing in the diagonal ensemble is that you have these coefficients, which Benjamin called Cj, I remember. This looks like a Gibbs ensemble. So if you are able to go to write it in this form, let's call it G. So by exponentiating these overlaps, then somehow you see it's similar to the Gibbs ensemble. But to do that, you have to calculate these objects. So first, you have to be able to calculate these objects. Second, you have to hope that when you exponentiate them, you can write this Gn in some way like, some density times some particle distribution, okay? In a way like this. Okay, so long story short, so for some states, like an L state or Majumdar-Ghosh states, simple product states, or states with low entanglement, you can do this. The expression on a lattice are really complicated, so they involve some complicated determinants. And then even more remarkably, you can do this continuum limit, and you can extract this Gn. And then once you have this Gn, you can plug into these equations, and you can try to solve it. And then you get a surprise because you, so even if you work with the Gibbs ensemble, you're not able to solve these equations analytically. And then a remarkable fact, in this case, so if you work with these overlaps, at least for some of the overlaps, you get closed expressions for these zetas and also for the rhos, which is, they are written somewhere. So you can, I think you can look at this. So, cool. Here is a nice summary of this idea. This is part of a special issue on quenches, which is of some years ago, which is also very nice to read. Okay. Good. Basically, now we have more or less everything. So we have the GG that describes the steady state, meaning that I have this rho whole, rho particle, and rho total. I can compute the von Neumann entropy. Then I can use this technology to calculate, well, the equation that I wrote before here, to calculate the group velocity of the quasi-particles, and then I can plug into the quasi-particle picture. So one important caveat is actually that, so one important ingredient of the quasi-particle picture, indeed, is that you have pairs. This is not guaranteed for a generic quench. So if you have an L state, you can argue that this is the case, and actually you can read this information from the structure of the overlaps. But for a generic state, it might be that the entanglement propagation doesn't happen just, I mean, because of pairs, but because you have more complicated objects. So unfortunately, we only are able to treat so far the case with the pairs, okay? And for the Nel state, for Majum de Gauche state, from some a few other states, we are able to apply the quasi-particle picture. Okay, so I think it would be nice now to have some figures showing the agreement. Unfortunately, I don't have it. So maybe, but I can give you, so I have the reference, so you can open it and you can look at it. So yes, it's funny that I cannot find my own reference, my own paper. Okay. So. So the results are there, so you can look and, I mean, within the numerical possibilities that we have, it seems that it's working. Okay. Okay, now I have a list of other topics that I can cover. So I think I will select some of them, and yeah, and then when time is up, I stop. So another thing, a thing that you can do is to study Renyi entropies. Okay, so far everything was for von Neumann entropy. You can work, you can try to understand what happens to Renyi entropies. So Renyi entropies are, yeah, let's call it 10 minus. This n I don't like, let's call it alpha. Now, for free Fermi, here there is a nice thing that happens. Actually, I think it's interesting. So, for free Fermi models, as I said, you can characterize the steady state via the occupation, fermionic occupation n of k. So you can write local observables or the von Neumann entropy in terms of this n of k. the thing is that for free fermions, the Rényi entropies are also written in terms of this n of k as well. So in fact, so you have that so if you want to get the quasi-particle picture for the Rényi entropies, you have just to substitute the density of entropy. Okay, so for the von Neumann entropy, you had a certain function of n of k. If you want the prediction for Rényi entropies, you have to plug in this other function of n of k. Now the question is what happens in the presence of interactions. Something I would say remarkable happens, and this is not true anymore. Okay, this comes really nicely there, because if you want to apply this formalism to describe Rényi entropies, what happens is that you have to the most naive approach is to study this equation by putting here this index alpha. This is a big effect. So you are rescaling the driving of the TBA by this number alpha. So, and the solutions that you get are completely different. Okay, the densities, the root densities rho that you get are completely different. They don't have anything to do a priori with the root density that you get by putting alpha to 1. Okay, in pictures, what happens is that if you have the spectrum of your integrable Hamiltonian, you have some macro state here that describes local observables, but also the dynamics of Rényi entropies. If you put this alpha here, and alpha is not 1, then you end up somewhere else with a different ensemble. So this is a bit surprising, because when you do, let's say, the numerical experiment, you run the simulation, you have the wave function, then you calculate local observables, von Neumann entropy, whatever you want, all from the same state. But here I'm saying that within this approach, so local observables and Rényi entropies are described by different regions of the spectrum of the many-body Hamiltonian. This is somehow a consequence of the fact that the system relaxes to an ensemble that contains information about the full spectrum of the Hamiltonian. And apparently, at least within this approach, Rényi entropies and local observables probe different regions of this spectrum. And I don't know, if you can try to do the same for free fermions. If you do the same for free fermions, actually, you can also write an equation like this, put the alpha and so on. If you do that, then you see that you can rewrite everything in terms of the n of k that you get for alpha equal 1. So somehow for free fermions, there is a simple functional relation between the n of k that describe the von Neumann and the n of k that describe the Rényi entropies. For interacting systems, this is not easy. At least we didn't find it. So, okay. So this is one thing that I want to say. Yeah. Yeah. Okay. So, I mean, it's they're kind of equivalent. So from the quantum information perspective, they encode similar information. So if you have a pure state, somehow they both give way to quantify how much entanglement you have. The Rényi entropies have a big advantage compared to the von Neumann because they are easier to calculate, let's say in field theory. There is a well-known formalism, let's say, that is called the Replica Trick, and you can use it to compute Rényi entropies in CFT or generic field theory. You can also access them in numerical simulations because you can basically, by simulating different copies of the same model, let's say with Monte Carlo, and by carefully choosing an observable which connects these different copies, you can actually measure this for one-dimensional systems, but also for higher dimensional systems using both quantum and classical Monte Carlo. Last but not least, you can measure this in experiments. So there are by now a certain number of groups that do that. So the group of Greiner in Harvard, in Innsbruck, they also do it. And then there is also a reason, a more theoretical reason that if you can construct these entropies for all alpha, then you can invert, you have a kind of moment problem that you can invert and reconstruct the distribution of the spectrum of the eigenvalues of rho A. And this, of course, contains more information than the single entropies. Okay. Yes. How much time do I have? Okay. Okay, and then I can just mention. So I have a long list of topics. So there are at least 3-4 more, but I take only one, which is related to what Benjamin will say. So now let's move to the inhomogeneous situations. Okay, so far everything that I discussed was homogeneous. So the initial state was homogeneous, and the Hamiltonian that you use in the quench is homogeneous. Now we keep homogeneity only in the Hamiltonian, so the Hamiltonian is still homogeneous, but the initial state is not homogeneous. Okay, so we have a left and the right part, and they are different. Okay, they are both homogeneous but different. So, for instance, they can have different energy density and so on, different number of particles, whatever. And you have the Hamiltonian, which is homogeneous. Now, so what happens if I take this Hamiltonian and evolve the state? So what happens is that you have a light cone. I think at some point Benjamin was drawing this on the blackboard. So here you have the origin. Let me write psi left and psi right, the two initial states. So here you have the light cone, and then what you have is that the model is integrable, so you have a ballistic transport, which means that if you look at an observable as a function of space and time, actually this, for large times and for large x, where x is the distance from the center, it will not be a function of x and t independently, but it will be a function of x by t, which I call z. So in this figure, you can draw rays. So each ray corresponds to a certain value of x by t. And the model is integrable. So you can invoke local equilibrium. So in each of these rays, the system will locally equilibrate. And since the system is integrable, each equilibrium states will correspond to a GG. Okay, so you will have a GG for each Z. And a GG now, it's correspond to some densities, which have this label Z. So now there are too many labels. So rho n, let me write here Z and lambda. Now, these GGs outside of the light cone, they have to be the GG that describes the homogeneous quenches that you have in these homogeneous situations, okay? In which you start from one of the two leads separately. So you have some boundary conditions that you know. But then you want to know what is the equation that allows you to get this rho as a function of z. And then, so here I think I should be, oh, I don't have the reference, oh my God, okay. So the nice result of Olaja and Ben and Takato, Yoshimura, and at the same time by Bertini, Collura, Denardis, and Fagotti, PRL, and the year I think is also 2007, something like that. is that you have a simple equation that you have to solve. Very simple. So it's an equation written in this form as a function of z. It looks a bit weird, but if you write it in terms of x and t, it's the continuity equation that Benjamin wrote today. And you see these velocities are the same velocities that I used for the Neumann entropy, okay, the same group velocities. So this equation is non-linear. It looks linear, but it's non-linear because this v depends on rho. And this you can solve. And you can determine all these GGs. So you have the full out of equilibrium dependence of a generic observable as a function of x by t, at least for large x and large t. Now, the thing that I want to discuss is what happens to the entropy. And now, let's say that you want to study the entropy between the two parts, left and right. Okay. Now it's very complicated because even though you assume that deep in the bulk you have the entangled pairs, what will happen is that these will have straight line trajectories if they're outside of the light cone. But then when they enter the light cone, their trajectories bend because here you have a different equilibrium state for each value of z. Okay? So now the problem is the same as before. In the homogeneous case, you have to count the number of entangled pairs that are shared between left and right. But since the trajectories are nonlinear, it's a bit difficult. And you can have funny situations. So let me conclude by saying this. So one funny situation is the following. So in the usual case, at long times, you have that the two members of the entangled pair end up in different subsystems, okay? So this is, let's say, now my A, and this is my complement. In this inhomogeneous case, you can have something like this, that at infinite time, both quasi-particles end up on the same side. And this is actually a really important thing because it's only due to interactions, because it's interaction that renormalizes the velocities. So these weird trajectories are only due to interactions. You can still compute the rate at which the entanglement entropy between A and A bar grows. Yeah. Yeah, of course, but you have, you have quasi-particles with different velocities because you have a dispersion, so yeah. Yes. And now, if you do the calculation, which is horrible, you end up with this formula. So something that I want to highlight, and I conclude, so this formula depends, so the rate at which the entropy grows, so first of all, it's linear in time, so the entropy grows linearly. Then the ingredients that you have inside depend only on a specific value of z, which is z equals 0, which is the GG that describes this interface here. And this is somehow expected because the entropy grows when these quasi-particles cross the boundary. So it's natural that the macro state is the one that is with z equals 0. But then there is this weird thing here. So there is this dependence. So in the homogeneous case here, instead of sine of lambda, you would have sine of v. And then you would get the absolute value. Here you have a sine of lambda. And this gives a non-trivial contribution only because you have this situation here. Okay? And with this, I think I can conclude, and I thank you for listening.